Without any further delay, I would just like to welcome Christopher Yao from the University of Oxford. He has currently agreed to deliver today's seminar. It's going to be about derivative-based neural modeling of cumulative distribution functions with applications to survival analysis. And I'd like to thank you on behalf of everyone, Chris, for agreeing to present. And yeah, the stage is yours, and we're looking forward to hearing about your work.
Okay, great. So thanks for the invitation, and sorry to those in Cambridge that I can't be there in person, but as those of you know, we've been given the runaround a bit with train companies in this country recently. I'm going to be talking about some work which has largely been done by my student Dominic Danks, who's based at the University of Birmingham, where I was previously, and some work by a new student called Natalia Hong, who's based in Oxford. And this is a new area of work for me because I haven't traditionally worked in survival analysis. And so my perspective on things maybe is a little bit slightly different from the traditional. So what am I interested in? So we're interested in doing time to event modeling. And in my case, I'm interested in developing risk prediction models. So what I'm interested in is measuring something about an individual, a patient, and then being able to calculate their personalized risk of experiencing some kind of event, or potentially one of multiple events if we're interested in competing risks. And I'm trying to really understand sort of the relationships between these kind of time to event distributions and these patient-specific characteristics, with the goal ultimately of being able to translate that into specific clinical actions that might be taken depending on individuals' personal clinical profile. So this talk is going to be mostly about some of the underlying methodology behind that, how we learn patient-specific risk profiles or competing risk profiles, but also focusing on how we might do this in a way that where we don't necessarily need to use some of the potentially quite strong classical assumptions that are used in this area, such as proportional hazards and Cox and other things like that. But we also want to think about models which also function across a range of small and large data sets. Many kind of modern approaches to this kind of problem kind of implicitly assume the availability of very large data sets, but very frequently in this domain, it's actually very hard to get very huge data sets, and we only have access to small data sets. And it seems unsatisfactory sometimes to have methodology, separate methodology for the large and small data domain. Can we build machinery that functions with both? So I'll give a quick overview of the recent kind of state of the art of what people be thinking about in this area shortly. Then I'll move on to talking about how we model cumulative density functions using the derivative models that I'll shortly introduce. And then how we can use these derivative models to then build single risk survival models and how these can be extended to competing risks. And strange but true, because as I said, I haven't classically worked in this area. I'm going to do this with very little reference to things like hazard functions or many of the conventional survival analysis terminology, partly because the methodology that we've developed doesn't require us to utilize these things. So here's a little bit of kind of background. Survival analysis, particularly in the machine learning area, has been an area of very intense recent research interest. And there's lots and lots of different types of algorithms or methodologies appearing. The table on the right just lists a few of them. This was out of date when I drew it earlier in the year, and it's become even more out of date since. So there's many types of different methodologies. The common themes underlying sort of recent research interests is this reduction of the reliance on classical modeling assumptions, and perhaps more so the making use of more recent kind of deep learning methodology in order to allow us to do more flexible, use more flexible approaches to model functions, but also to allow us to tack these survival models onto other models which are processing more complex types of data, so what people might call multimodal data integration. So this might, for example, be trying to learn directly from images or natural language text models, something that can then be fed directly into a survival model and can be trained all together or fit all together at once rather than as two independent models. But this recent sort of surge of research interest has led to lots of different methods, lots of people using different types of modeling assumptions, which therefore then lead to different capabilities. And functionality is constantly evolving. The methods are getting better over time. But one kind of constant has been that it's been very difficult to kind of validate these models, and there's a limited number of appropriate data sets. And some of the tools that we have to measure performance are not particularly ideal. And I'll spend quite a significant part of this talk talking about the ways that we've kind of addressed this. So we kind of started off on this venture into this work and not really thinking necessarily about survival analysis, but thinking about non-parametric density estimation as a kind of general statistical problem. And one of the things we kind of thought about was how do we model cumulative density functions? We know what a cumulative density function needs to look like. It needs to start at 0, it needs to be monotonic, and needs to asymptote towards 1. Can we construct a model that has a sort of large support over sort of valid continuous CDFs, but otherwise has minimal additional constraints, and essentially use that as a kind of prior for our modeling purposes and our learning kind of purposes? Now, obviously, this is not a new problem, and many people have looked at this before using many different types of approaches. It could be things like mixtures of some kind of basis function, which sort of underlie kernel density estimation methods, or mixture models, which have been very popular. If you want to go, fully Bayesian non-parametrics, you might start playing around with various types of stochastic processes that admit random probability measures. Or you can make use of things like Gaussian processes and neural networks, constraining them in some way so that they can directly approximate cumulative density functions, or equivalently probability density functions as well. The work I'm going to talk about sort of builds on a fairly classical idea that has been around since the 1950s and 60s, which is that the solution of certain types of ordinary differential equations, or ODEs, actually correspond to valid probability density or cumulative density functions. And what we're using is actually quite a simple and straightforward idea, but turns out to have, as we found out, quite a lot of practical and useful applications. So the idea is quite simple. How do I model a cumulative distribution function and do so by a differential equation? Well, what I know is if I can define a derivative function, which is always positive valued, and then I can solve using that derivative function to get back into the original domain, what I can guarantee, if my derivative is always positive valued, is that the function I get after integrating out is always going to be monotonic. That's great. That satisfies one of my conditions that I need for a valid CDF. Now, the problem is that monotonic function is not necessarily going to be bounded by 1, but what I can do is, of course, I can scale that by warping it in some way, and what we use is a hyperbolic tangent function to do that. So if I can scale that monotonic function in some way, then the result is that I will get a valid cumulative distribution function. Now, if I parameterize that original derivative function here using some parameters which I've denoted as theta, and that those parameters are adjustable, then if I'm given some data, I will be able to kind of tweak those parameters according to some kind of loss function or likelihood until the cumulative distribution function that I get out after sort of integrating out this positive value derivative function will be a good fit to whatever data I've using. So this very simple idea of defining these positive valued derivative functions, solving them, and then scaling them in order to make them into valid CDFs, and then doing so in such a way that they're parameterized so that I can do some kind of learning, whether it's Bayesian or optimization based, seems quite an attractive idea. And so how do I define these derivative functions in a flexible way so that allows me to model all kinds of possible cumulative distribution functions? Well, the way we've decided to do it is to use a neural network. In our case, it's probably going to be a deep neural network with many sort of layers and many units to give it the expressivity to allow us to model a large family of valid cumulative distribution functions. And I can always make sure that those neural networks have positive range by essentially slapping on something as an activation function at the end of that neural network to make sure that anything emitted out of that neural network is positive valued. In this case, we're using something known as a soft plus activation function. So if I can model my derivative function using this positive valued neural network, I can then integrate out that differential equation numerically. We use Gauss-Legendre quadrature to do that integration. That will give me this monotonic function u. I can scale that using some wraparound function. We're going to use the hyperbolic tangent, but other choices are possible. And if I do all this, I know that what I get out is a valid cumulative distribution function, and one which I can tune by essentially learning the neural network weights in my derivative function in such a way that I will match whatever data or problem that I'm interested in. So, for example, if I'm using this purely for density estimation, suppose I'm given sort of n independent and identically distributed samples from some kind of continuous distribution. Well, how do I sort of learn what density that those samples come from? Well, I can use my DE-CDF model. I can define my negative log likelihood for this particular model, and is shown here as equation 2, and has a relatively simple form, and it stems from the fact that we use this hyperbolic tangent, and the derivative of the hyperbolic tangent has this convenient form of 1 minus the hyperbolic tangent of x squared. So that's kind of convenient. We didn't have to use hyperbolic tangents, but it makes some of the mathematics more tractable and nicer. So I can use this model and derive a likelihood from that model. Once I've defined that likelihood with respect to these neural network parameters theta, given the data, I can fit this model to that particular data using any sort of appropriate optimization technique. But because we're building these using deep neural network frameworks, all optimization is done using a mini batch stochastic gradient descent, or the atom optimizer. So here are some examples where we've just used this simple model as a pure 1D density estimation technique. So the graph on the left here shows some fits to some data which have been just drawn from standard distributions. So these are just 1,000 samples on the left-hand side, drawn from either a Gaussian or two different parameterisations of a Weibull distribution, and these show the CDF fits to those draws and the corresponding PDFs, which we can just derive from once we fitted the cumulative distribution functions. So we can fit relatively simple standard distributions. Can we fit something a little bit more complicated? So on the right-hand side, we've just drawn 1,000 samples from a mixture of Gaussian process, a mixture of Gaussians, where we have two components with different sort of means and same variances. And we've fed those draws into our DE-CDF model, did maximum likelihood estimation, and then come up with a density estimate, which closely approximates what the ground truth should be, and is very comparable to an equivalent technique based on Gaussian kernel density estimation. So now we have some machinery that allows us to model cumulative distribution functions in a sort of non-parametric way. Can we make use of this in a way which is useful for survival analysis? So here's the kind of standard kind of setup. We have data for a number of individuals where we have some subject-specific covariates X. We may have S, which denotes the time to an event. And we have an indicator K, which is denoting whether the event has actually happened or not, or in this case, whether it's been right censored. And the goal is to learn a survival function here, ST given these covariate X, and where the individual survival is modulated by these covariates. The interesting part for us is that this F now, or S altogether, can now be defined using our derivative CDF model. So the approach we're going to take is slightly different to conventional kind of approaches to survival models. We're not using a parametric approach like an accelerated failure time model because ours is non-parametric. We're not using semi-parametric models like Cox regression, where things are defined, where covariates enter into things via the hazard function. We just don't have that. We're modeling actually the survival functions directly and their relationships with the covariates. And we're not the same as other sort of neural network or deep learning based models which have been derived recently, which are extensions of Cox, where instead of having a function which is linear in the predictors, they wrap some neural networks around the covariates and make it a non-linear dependence of the hazards on the covariates. Instead, as I said, we're just directly modeling the cumulative distribution functions and learning the mapping from our covariates to those directly. So how do we do that? Well, we simply just need to extend the inputs into our neural network, which defines our derivative function. So now instead of G just being having a single input of time, we're going to augment it with the covariates that we're interested in. It will still have some parameters, phi in this case, associated with it, which are the neural network weights that we'll need to optimize. And so if we just simply follow the previous logic of defining this positive value derivative function in terms of this neural network, which has these two inputs, the X and T, if we solve for U to get this monotonic function out and scale it using the hyperbolic tangent, then I will get a CDF-F, which I can use as part of my survival function. So the extension from that previous case to this slightly more complex case where I have covariates is actually quite straightforward. We just need a kind of bigger neural network to accept the extra inputs. Similar to before, we can define, given that we have this model, we can define a likelihood for the model. Taking into account that some of the events have occurred for some individuals and some haven't been censored. And once we define this likelihood, of course, given any kind of data, we can use this likelihood as an optimization objective and apply our numerical optimization in order to identify the neural network parameters which best fit a particular data set. If we really wanted to, though, you can get classic identities out like the hazard function in this particular case, because again, we use the hyperbolic tangent. The hazard function turns out to have a relatively simple form, which is also actually relatively easy to compute. So in this case, the hazard function is 1 plus this CDF f times the positive value derivative function. So once we fit the model to get the hazard, we just need a single forward pass of the neural network that tells us what our derivatives are, and one forward calculation of the CDF, which can be computed using numerical quadrature. So what happens if we have multiple risks? So we have competing risk settings, and now K can be any one of capital K events. Well, in this case, for those who are familiar with competing risks, then what we need to model is a series of cause-specific cumulative incidence functions, one for each potential cause that may be relevant to our particular problem. And in this particular case, it's actually, again, fairly straightforward for us to extend the methodology I've described to this particular setting. Now I'm interested in a cause-specific cumulative incidence function. So I'm interested in the joint probability of T, given the covariates X, but also in K as well, which particular cause led to that particular kind of event. I can factorize that out as a conditional CDF of the event time given a particular cause and the covariates. I can model that as a particular conditional CDF. And I need this weighting, which is the probability of a particular cause given the covariance. And I need to make sure that those weights add up to 1, because of course, one of those causes all those causes, the sum of overall those causes must add up to probability 1. And because I have this, derivative-based CDF machinery, I can just directly model each of the cumulative distribution functions without having to use things like cause-specific distribution functions and things like that, which may have been classically used in other types of models. I'm just going to go directly for the CIFs and model these. I can also model the weights here, the pi's, for each of the causes, again also via neural networks with constraints, so that the probabilities which are produced are guaranteed to add up to 1. And what I've just kind of described is sort of best illustrated in the picture that I'll show shortly. But for this competing risk model, we can equivalently write out a likelihood for that particular model, which we can then use as the basis for fitting this model to any given competing risk data set. And what we're doing with this particular likelihood is fitting all K cause-specific cumulative incidence functions simultaneously, and in doing so ensures that the all cause probabilities will add up to 1, which is not necessarily the case, as I will describe later, with some models which have classically been used for this type of problem. So here's kind of a graphical illustration of how this all works. So the input into the model will be, a survival time, but we're interested in calculating these risk probabilities at. There'll be individual covariates X. These are going to feed in to create these monotonic functions U, one for each particular cause that we're allowed for in our particular application of interest. And this mapping between the inputs and these monotonic functions is going to be via this derivative-based approach, which I've described. In the competing risk setting, I also have these additional weights, which are telling me what's the probability of each of the different causes given these covariates. I can use something known as a softmax neural network to map these inputs directly to these weights, and then I can tune the weights of these neural networks to adjust these weights, and this is what the learning process will adapt given any particular data. And then I can combine these monotonic functions with these weights. The monotonic functions will be scaled using the hyperbolic tangent to give me cumulative incidence functions for all K events. And if I have these weights, I can also combine them to get the all cause probabilities as well. And this model is nice because it can be what machine learning people called trained end to end. So again, given any data, all the parameters can be estimated using maximum likelihood through stochastic gradient descent and fit all simultaneously. So does the model work? Well, what we did was we followed conventional kind of practice in this area and defined a series of different real world data sets that we can test our models on. In this particular case, we used 4 different data sets, one called Metabrick, support, a synthetic data set with 2 different causes, and then fourth data set was SEER, which was real, but we're looking at competing risk between breast cancer and cardiovascular disease, all with different kind of sample sizes, different degrees of censoring, and different numbers of features and other types of characteristics. And what did we find? Well, we found that for certainly in the single risk setting, that our kind of method did quite well compared to what is available out there. Based on a number of metrics which are commonly used in this particular area. Across these different metrics, we did quite well. If bold shows that we outperformed the others. But on concordance, for example, which is a measure of performance, which tries to measure whether you are, if I experience an event at a particular time, the idea of concordance is that I should then be assigned a higher risk than someone else who at that particular time T has not experienced that event. And so concordance is kind of a measure of whether your method has ordered patients or individuals correctly in terms of their risk probabilities. So we don't do quite as well as one of the other methods called deep hit, but that's not surprising because actually deep hit in its conventional form is designed to target that actually as an objective. So it tends to outperform the others. But on the other kind of measures, such as integrated Brier score, and I won't go into this too much details, which tend to look a bit more at the calibration of the risk probabilities, we tend to do quite well. There's an argument here as to whether in absolute terms, any of these numbers make a substantial amount of difference. And then this is something I will discuss more in detail shortly. But if you want to look at, sort of examine some of these survival functions, which are estimated, in top left here is just standard Cox proportional hazards. Top right is something called known as Cox time, which is one of these kind of deep learning methods which slightly extend the standard Cox model. Deep hit on the bottom left, which is this method which optimizes against concordance, is shown in the bottom left here. That's a full sort of neural network based model, and ours is given on the bottom right. And what you should kind of take away from this kind of picture is that actually, it's kind of reassuring that our method doesn't look fundamentally that different from the 2 Cox methods in terms of what survival functions is produced for these 5 randomly chosen patients. What's kind of interesting is that because deep hit calibrates primarily against concordance, the calibration of its survival functions looks a little bit off. The ordering is right, but perhaps the calibration doesn't quite look correct. And this is a fairly well-known phenomenon, and it's a byproduct of optimizing against the concordance index. We looked at a different data set support and found kind of similar things. We do particularly well on many of the metrics. And if we look at some of the survival curves, similar kind of things can be observed. There's kind of a strong relationship with us and some of the methods which are based on Cox, which is a symbol of how well the Cox proportional hazard still works for many kind of problems, and there's maybe some calibration issues with something like deep hit. When we went to sort of competing risks data sets, though, things started to get a little bit more interesting. So we looked at these, one real data set, the SIA data set, and a synthetic data set that was actually used in the original DeepHit paper, which they used to sort of test performance. And what we found was actually, in terms of concordance, actually DeepHit did better than us on the real data set SIA, and we did slightly better on the synthetic data set. And we couldn't really go into a huge amount, much more detail in terms of understanding why this was. On the synthetic data set, part of the problem was that a lot of this synthetic data was kind of clustered around time 0, and because DeepHit sort of discretizes time, the time grid over which it was estimating over perhaps wasn't fine enough, so we sort of adjusted for that and its performance improved. But with the real data set, SIA is a real world observational data set, it wasn't really quite straightforward to understand why there was a difference in performance, other than the fact that DeepHit is designed to be optimized on concordance, so it has a natural advantage over the method that we've proposed. We could look at some of the survival functions, which are kind of estimated from that SIA data set, but again, without a sort of ground truth, it's very difficult to kind of understand, what is real or what is not. And similarly for the synthetic data set as well. So despite sort of the uncertainties around the competing risk performance, actually we got our paper accepted into AI Stats earlier this year. And it was great, and we were accepted for the conference publication, and there was some evidence that our method was doing quite well for the problems we wanted to address, and certainly from a kind of machine learning community point of view, it sort of met the bar for being useful. But I was kind of personally sort of not quite satisfied, with this. There's something not quite right here, and the measures that we're using to assess performance didn't seem to be that great. And when we're only benchmarking on real world observational data sets, there's no ground truth. So how do I know, what I fit is actually calibrated and it represents the real truth? And we're kind of looking around for different measures to examine, to assess the calibration of risk models in a competing risk setting. And then we came across this paper by Peter Austin earlier this year, and realized why we couldn't really find any relevant measures. And it turns out that actually this area has been given relatively little attention, and there wasn't that much available for assessing calibration. So we decided actually that what this area of work needed was, ground truth kind of data. So we set about, my student Natalia did this work, was to sort of generate, very realistic data to test our methodologies. It's not real data, but it's pseudo-realistic. Using a multi-state process approach, which some in the audience may be highly familiar with. We set about sort of, really making an effort to, model different kind of competing risk settings, defining various cause-specific hazards in a way, simulating data in different kind of scenarios. So here on the right-hand side, it's just a straightforward scenario where you go from baseline to having one of the k different kind of conditions. But then we also simulated much more complex situations where we might have a series of states, and we're modeling the life course acquisition of different conditions for an individual. And this is partly inspired by the fact that we're doing some work in multi-morbidity, actually with people at BSU, with Sylvia and Paul. and looking at how multimorbid individuals, how their sort of outcomes differ from those who don't have multimorbidity. So we wanted to simulate some more complex scenarios like that, and we set up models to enable us to do this. And the ultimate goal was to sort of create some synthetic data sets, which for us was to mimic UK primary care data. So this is just an illustration of some of the synthetic data that we generated for lots of individuals. We might have characteristics like age, BMI, and gender, and various kind of additional features, which might be blood pressure measurements or various other physiological parameters, as well as the conditions that they acquire over time. So mimicking very much a GP record for these individuals. And the great thing about creating these hopefully quite realistic data sets was we then actually had a ground truth. So we know exactly how the data was generated. We know what the various risk functions should be and the cumulative incidence functions, etc. And so we actually have something concrete to measure against. So this is a table now comparing some of the competing risk methodologies against our sort of standard metrics. And what we find is that there's quite variable kind of performance across the methods, across these 5 repetitions of one of the simulations. This a simulation based on the kind of simple competing risk model. And we were looking at this and feeling a bit kind of puzzled at the time as to why performance was kind of so unstable, or want for a better word, across different types of methodologies. And in particular, what was interesting is that if we put in the kind of the true model into our benchmark, it didn't always come out as the best kind of model. And when we looked at more complex kind of simulations, like our multimorbidity simulations, different kind of patterns kind of emerged. Our method seems to be doing a little bit better than some of the others, but again we found that true model didn't seem to be doing the best here, and that seems not right at all. And it kind of made us think, and that something wasn't quite right. But fortunately, some colleagues of mine, David Steinerstolz and Dino Sinoidovich in Oxford, happened to be working on this problem at the same time. And they wrote a paper also published in the same conference, actually conveniently, where they looked at whether these standard metrics, which are used to assess these methods, were actually proper scoring rules. And it turns out that most of them, actually all of them, are not proper scoring rules. A proper scoring rule is something that, as a metric, where the true model should always actually perform best. And it turns out that things like concordance and integrated Brier scores, which are commonly used to assess these methods, are not actually proper scoring rules. And what they found in that piece of work was that many of us in the audience would intrinsically agree with this, is that really what we should be comparing is some form of a likelihood across the methods. But there's a difficulty here, is that many of the competing risk models that we might want to use either are not likelihood based, so there is no likelihood which we can use, or if there is a likelihood, they haven't necessarily implemented it in a way that allows us to to use those likelihood values, and that's because in the implementation they may be just missing some constants in the likelihood calculation, or because some of these methods are discretized, so they operate over a sort of finite time grid, we kind of have to interpolate in order to get likelihoods at different time horizons. So instead, what we did for our simulations, because we actually have the true cumulative incidence functions, because we generated this data artificially, was to define two different scoring rules, which are proper, which is simply just to look at the error between the predicted and the true CIFs, and taking the average of those mean integrated squared error or the mean integrated absolute error. For some of the methods, as I said, we need to do some interpolation because they only produce outputs on a finite grid of time points. But if we use the proper scoring rules, then we can actually kind of see a much more clear kind of pattern emerge. In the simplest situation where we just have a straightforward competing risk model, actually all the methods do quite well. Fine-grained this particular does the best, but actually in absolute terms, everyone does quite well in that kind of very straightforward competing risk scenario. When things get a little bit more complicated and we were simulating conditions according to kind of the life course events and the correlations in the inputs, then the non-linearity of our method, the DeSurv, which we call, but also random survival forests, is really quite helpful. Actually, fine-grained does quite well in this setting as well, but there's a slight problem which I'll discuss later. And really, when we go to a setting in which where we deliberately introduce non-linearities between the predictors and the risk prediction risk functions, then of course our method has considerable advantages. So these are just some illustrations of the risk functions produced in that simplest setting where we just have a standard computing risk simulation model. And this kind of setting, most of the methods estimate the cumulative incidence functions across the 5 different causes that we simulated really rather well, and fine-grained in particular does the best on average, which is not surprising as this model was almost identical to what fine-grained assumes. When we went to the more kind of challenging situation when we're simulating these kind of life course multi-morbidity trajectories, things got a little bit more interesting. Fine-grained started to have some problems. And if you kind of look carefully on the left-hand column here and sort of add up the core-specific CIFs, the probabilities produced, what you'll find is that they add up to more than 1. And anyone who's sort of familiar with fine-grained computing risk models will realize that actually for some covariate patterns, the sum of the core-specific CIFs can actually exceed 1. And Peter Austin and others have written a paper on this last year, although the problem has been sort of around in the literature between practitioners for quite a while. Most of the other methods are fine. They're constrained to avoid this kind of issues and give reasonable estimates of the CIFs, although of course our method tends to do best overall. When things go not very non-linear, then of course our method, is at this sort of in this area of strength. In this particular case, you can see that causes 2 and 3, the CIFs are quite sharp, and it's very difficult for the other methodologies to model that kind of sharp transition in the CIFs. But for our model, this turns out to be not a problem, particularly if you have enough data points. So we simulated like 10,000 individuals in the simulations. Things might be a little bit different, of course, if the sample sizes are smaller. So just to broadly kind of conclude, what I've talked about is this kind of framework, which we call DeSurv, which uses this derivative approach to modeling CDFs. What this has allowed us to do is think about doing survival analysis in a slightly kind of different way. The framework allows us to build models which are continuous in time, which is not always the case when modern sort of deep learning approaches have been used in this particular area. By directly modeling the CIFs, we actually have quite a simple approach for dealing with competing risks. And this non-parametric approach to modeling the CDFs means that we can relax a lot of typical classical assumptions. All of this can be integrated in one model, so it's all done under one hood. And you don't necessarily need to have separate models for different regimes. And it's been achieved primarily through, as I said, direct modeling of the CDFs rather than going through the approach of modeling kind of hazards. The main advantage, and I'll talk a little bit more about this very shortly, is that with this neural construction of this survival model, we have the opportunity here to plug it into other neural models. And I'll talk more about how this might look right at the end of this talk. Our work is not completely new. There have been related approaches, and Jung and Fine in 2006 and JRSC essentially did what the parametric version of what we do. They did. They looked at models where you specify parametric forms for the cumulative incidence functions, and you end up essentially with the same kind of framework without the advantage of the flexible functional modeling. Almost sort of in parallel with the work that we did, the group at Oxford, Rind et al., produced something known as a SumoNet, which uses a similar idea of using monotonic neural nets to model CDFs. Instead, in this particular case, instead of using differential equations, they used something called MOND, which was produced by Chilinsky and Ricardo Silva at UCL a couple of years ago, which uses constrained neural networks to model cumulative distribution functions. And what's nice about that, which we don't do, is that Ricardo's work sort of links in with some of the work that he does with copulars. So MOND allows you to model multivariate cumulative distribution functions and generalizes things a little bit further. There's also some connections, which we describe more in more detail in our paper, which I won't go into do now. But the process that we use has some links with the use of normalizing flows. And if you're interested, you can read more about that in our paper. There are limitations to what we've done, and the first of these is explainability as an approach that uses neural networks to kind of map covariates onto, in this case, risk functions. We inherit the kind of general issues around this type of machinery in terms of interpretability. Isn't quite straightforward for us to understand what the effect of an individual covariate is on the output. There are potentially a lot of parameters to optimize in our models, particularly if we want to, have large neural networks in order to have more expressivity and to cover sort of wider range of possible CDFs. So there's a need to optimize a lot of parameters and a lot of hyperparameters, and these can be critical for the performance of neural network-based models. There are no uncertainty measures in the way that we've done inference. We've just done with maximum likelihood. And there's some questions around whether the model can be embedded within a Bayesian framework and posterior inference applied. Actually, embedding it within a Bayesian framework is fairly trivial to write down. It's actually just doing a posterior inference in a way that is meaningful, which is the tricky part here. There are also some kind of practical issues. All of our work is coded and implemented in PyTorch. It's a modern sort of deep learning framework. Really difficult to actually then use for some real world data sets where they're housed in trusted research computing environments, for example, where you don't necessarily have even Python, let alone PyTorch to use it on. So some practical issues here that go with the technology that we've used. And although we went to an effort of generating these pseudo-realistic data sets, it would be good to see be able to evaluate these models on real world benchmarks, but there isn't many of them in this world, or at least not many which are publicly available. And as a community, and particularly in the machine learning community, there's a danger that we are overfitting models to the same benchmarks, giving it a sort of biased impression of the actual performance of the methods that we're coming up with. So I'll end soon with a little bit of a preview about as to how we're kind of using and taking this work forward. We're developing something known as a neural joint longitudinal survival model, which is essentially coupling the survival model which I described to something known as a neural ODE model. And what this neural ODE model is trying to do is trying to process irregularly sampled longitudinal health records. So instead of treating the input covariates as some kind of static cross-sectional measurement, we actually treat it as an actual time series, which may consist of different measurements, blood pressure, measurements over time, different diagnoses, different medications. We're using a sort of neural network machinery in order to distill that into low-dimensional latent quantities, which can then be fed into our survival model, and then we can fit both of these things end-to-end simultaneously. So essentially, the kind of non-parametric equivalent of some classical statistical models, like the work that's been done by Dimitris Rizopoulos, where you might have a linear mixed effects longitudinal submodel coupled to Cox regression, which is what underlies his method called JM Bayes. But we're just doing the kind of non-parametric version of that, where we don't assume linearity and with mixed effects, and we don't assume Cox on the survival end. And early results that we've sort of developed, again, using this kind of pseudo-realistic data generation approach in order to help us evaluate performance, are showing kind of promise, in the regime where JM Bayes should work well when the data is simulated according to linearity assumptions and according to Cox proportional hazards. It does really well. But when things are non-linear or they're non-Cox, then our method does better in terms of these proper scoring rules that I've defined. So if you're interested in using or learning to use these kind of methods, the paper is available. Just Google for this, and the software is available on GitHub. It's quite intuitive, so if you know a little bit of Python, it's not too difficult to work out how to use it. And we'd love to hear feedback on people using it in different situations. So thanks for listening, and special thanks to Dominic and Talia, whose work this talk was based on. Thanks also to Krish and Kumar and his team at Birmingham, who supply a lot of the real world data that we use for the GP care, for the GP electronic health records. And this work was funded by EPSRC, MRC, and NIHR. Thank you.
Thank you very much, Chris. That was very interesting. Wondering if there are any questions from the audience. I can see Sean has one.
Hello there, Chris. That was really very, very interesting indeed, and I thought it was very clear. I just want to ask about a few practical issues in using this. So these hyperparameters that you have to optimize, they're presumably things like the amount of smoothing or shrinkage and the number of layers and the width of the layers. And I just wonder, how do you go about optimizing those hyperparameters? And if I may add a second question, which is connected in a way, how long does it take to run this software? And how big, this is a third question, sorry, how big does the data set need to be to use it?
Yeah, so you in terms of the hyperparameters, yes, I'm using as a catch-all term for all these things, both the architecture of the neural nets and then the consequence parameters. There are, of course, one or two tuning parameters in there to do with potentially to do with smoothness or to balance various terms as well in the loss functions. There are two answers to this. The classic machine learning approach is to take a data set, split it into all sorts of wonderful ways, refit your model multiple times, and then essentially do a very sophisticated form of cross-validation in order to fit this. That's the kind of brute force way. And if you do this, then it can take potentially quite a long time on a sizable data set to do, not because each iteration or each pass through the data is slow, but because you're having to do it so many times, potentially tens of thousands of times or millions, in fact, to optimize these parameters, it can be quite a substantial exercise. One of the reasons why we kind of designed the model the way we have was to kind of avoid some of this kind of issue where because we're able to directly model the CDFs and we have some control over, what does the derivative function look like and does it make sense? Is it smooth? We don't want, erratic looking derivative functions. It gives us a little bit more control actually as to what this, the CDFs that we model get out, which in effect reduces some of the number of hyperparameters that we need to kind of work with, and that kind of helps us a bit. But there are some parts of our machinery where it's just a neural network is taking in some input, it's spitting something out, and there are some weights, and it just needs to be tuned in such a way, using some of these brute force kind of techniques. In terms of how long it actually takes to compute, if it's a data set of size 10, 20,000, it can just be done on a laptop or desktop computer if you wanted to. So it's not horrendous. It's not instantaneous, obviously, because potentially you need to do these hyperparameter optimizations, but it's not necessarily huge. Obviously, when we move into like CPR, DGP practice level, with millions of individuals, it's quite heavy, but then that would be the same for all methods. I forgot the last part of your question.
The last question was just, what's the kind of minimum number of events that you need to be able to use this method?
This is something that actually Natalia is kind of working on at the moment. We've mostly tested in a regime where we have kind of several hundred or thousands of individuals and a fairly sizable number of events within a proportion of events within that. We're interested at the moment in driving that down and assessing performance. So hopefully we'll be able to give you the answer soon, but you may want to test it out yourself.
Thank you.
Any other questions? Perhaps I can ask Chris whether it's possible to use your methodology for causal questions, or how would you go about it?
I mean, we've purely built methodology for a predictive model, so we wouldn't necessarily use it for answering kind of causal questions. One thing I didn't mention, there was a series of simulations that we did where we looked at diagnostic delay. We deliberately introduced diagnostic delay into our synthetic data sets, and also oversampling. So people who are more ill tend to exist more in medical databases than people who are sick, because you want to go to the doctor because you're sick, so you tend to be overrepresented. And in those simulations, if we generate data, where these things are in place, then actually pretty much all the methods collapse. They just completely misestimate the cumulative instance functions because of this bias in the sampling or the diagnostic delay. And I think in order to account for those, we will need to actually use some kind of causal modeling to adjust for the fact that there may be some of this. bias sampling or diagnostic delay in there. But as it is, it's not, it's purely predictive model. It's not useful for answering causal questions.
Thank you very much. And I can see Sida has a question. So
yeah, thank you, Chris. Very, very interesting research. I have a quick question on how do you, so you mentioned about you call pseudo-realistic data generation. For instance, in the case of multimorbidity, how did you, can you give a little bit more detail on how you achieve that simulations?
So, you know, it's very similar to the work that you did, Cedar, which I, you know, with the multiple.
Because one thing I'm curious about, because you have a neural network, so I suppose that you train.
Oh, for the simulations, we're not using a neural network. We're just using a multi-state model.
Okay, I see. So you're not simulate from a neural network.
No.
Kind of thing.
In fact, all the transitions will be parametric.
Okay, I see.
Some form. It's just that sometimes they're parametric. Sometimes we tweak it slightly so that it's parametric plus something else, which makes it slightly kind of nonlinear, or the nonlinear predictors. But in the simulations, it's just a multi-state model simulation.
Okay.
Where it's to make it a little bit more tractable, we bias it slightly so that certain trajectories are overrepresented and some are very unlikely, as you would have seen in real life.
Okay, and for the model you use, this neural-based model, is it also easy to simulate from?
The once it's
trained,
once it's fit, it's easy to simulate from. Obviously, if you want
kind of the same philosophy to simulate. We have the CDF, and then you can invert everything.
So once it's fit, you can simulate straight out of the box. The parameters don't mean it, you know, aren't tuned, so you wouldn't be able to simulate.
Yeah. Okay. All right. Okay. Thanks.
I can see Thomas has a question.
Yeah. Hi. Hi. Thanks, Chris, for the talk. I just had a question about your proper scoring rule that you're using. One of the things that you said about deep hit was that they kind of incorporate the concordance into their loss. So and then by assessing themselves on that, they're kind of like readying them up to like do particularly well with that with respect to that index. With the proper scoring rule that you're using, that was assessing directly the cumulative distribution function. And because that's also what you're targeting, do you think that you're choosing a metric that you're more likely to be successful with?
I mean, yes, the answer is yes, but I think because the target is what we're interested in, you know, we are interested in that, you know, those risk functions is the appropriate and natural thing to use. Ideally, as I said, we would use, you know, something which is highly related to that, which is likelihood. But we couldn't in this case because not everything that we compared against had a likelihood. If you weren't interested in the risk in the form of the risk function, then of course what you suggest may be true, but it'll be a bit strange if you're doing survival analysis and you're not interested in the risk function. Yeah, and an extension to that is, I suppose, if there were versions of the other indices that had the problem that they weren't proper scoring rules, but if they were somehow proper scoring rules adapted in some way so that they were, I suppose that might be something you'd be really interested in. Yeah. I mean, it's not something we've looked at in particular, but I'm aware of some work. I can't remember who's been doing it, you know, in these kind of areas. And it will certainly be really useful for benchmarking against real world data sets. That's where we're lacking at the moment. So we've kind of got skirted around the issue by, you know, trying to generate pseudo realistic data. But again, at the end of the day, we still control the parameters, and it's close to real, but not real. But you know, some of these emerging kind of modified scoring rules, which are not necessarily completely optimal, but close enough, and would be really useful. Thanks.
So I can see Daniel has a question.
Yeah, thanks. Thanks, Chris. I was just wondering, you mentioned cross-validation. I was wondering, do you think that those sorts of approaches could be informative in some of the tables you showed that were comparing methods to sort of unbiasedly compare the methods?
I mean, certainly it's possible. I mean, I'd say for, the cross-validation procedure to optimize particular methods can be applied to all of them. And, all the methods have their own, unique set of parameters that need tuning. And I wouldn't say we've exhaustively looked at, everything, because sometimes it's not quite kind of obvious how we do those for particular kind of methodologies. So there's that. There's potentially some kind of cost validation based approach as a sort of validation technique, which is what you're kind of alluding to. We haven't thought of a particular way in which we were quite satisfied, that it would, make sense for us. But if you have any ideas, we'd definitely be happy to kind of talk about it.
Yeah, I think just I was kind of thinking like splitting into a test and training set, and because I was wondering whether some of those some of the metrics that were when you have some of those issues with the ground truth not performing as well as the some of the methods, whether there might be some sort of overfitting going on that could be mitigated by testing on held out data.
Yeah, I mean, a lot of our tests are calculated on held out data anyway.
Okay.
But I think it's a case that's related to what I think Thomas mentioned about earlier, that there may be a different scoring rule in which the way you split, is actually adaptive based on the type of events or what's actually in the data to remove that potential bias that's associated with that kind of scoring rule.
Okay, maybe I misunderstood. All right, thanks.
So I can see that we are out of time. So I'd like to thank Chris on behalf of everyone for a very interesting and clear talk. And yeah, we're looking forward to seeing you in person for the next time. Thank you very much again for presenting to us.
Thanks for having me. Bye-bye.